discussions also based on that later. So maybe things will become a little clearer once we look through these conclusions. But the most part of today's class will be towards formally introducing the variational asymptotic method. Of course, we have touched various aspects of it through the course, but we will formally introduce it, what it means in terms of a general mathematical procedure. So we will apply it to a very simple example, and then we'll apply it probably to the beam example a little bit in today's class, and following it up with Tuesday's class. So the idea here in terms of warping is basically it's some kind of a bridge between the 1D and 3D modeling that we have. Of course, you know that a beam, like any other structure, can be modeled as a three-dimensional structure on the whole. So you don't even need to have a dimensional reduction, just that the computational efficiency involved is not something which is acceptable. So there is something which is a 3D displacement, which we shall denote by uppercase U. Of course, we'll use this U for the strain energy some places, so but I'll avoid the confusion. But note that this is a vector field, and so it is in bold. And we'll also have the 1D displacement field, which is basically the translations in the three directions of the reference cross section, or you can think of the change that has occurred from the reference curve in the undeformed to the deformed configuration. So the 1D displacement is by definition a function only of x1, while this is a function of all three spatial coordinates x1, x2 and x3. And warping is also a three-dimensional field. Not only does it have three components along the three directions, but each of those components or measure numbers are functions of all three spatial coordinates. So before we relate these two quantities, utilizing the constraint that we introduced in the end of last class, we'll first look at certain aspects of warping which will enable us to establish this relationship. So first of all, one aspect about warping the vector is to be understood. It's a three-dimensional field, as we said. So this is immaterial of the cross-sectional reference system that you choose. So irrespective of what kind of a small b system that you choose, note that the measure numbers W1, W2, W3 are along small b1, b2, b3. But the vector W itself is immaterial of the choice of the cross-sectional reference system. In this sense, it is what we call as intrinsic field of the beam cross-section. And we'll look at a few other quantities which are intrinsic as well, and also a theory which is intrinsic as well. We will touch upon those aspects on Tuesday. But as of now, this is a good situation or a good example where you understand the warping very well, and therefore the introduction of this term intrinsic through this example might be appropriate, so that you can appreciate other intrinsic quantities later on. The idea is that anything which is immaterial of the choice of the reference cross-section or this reference system which is being used to depict it is basically something which is inherent to the problem, which is natural to the problem, and therefore not something extraneous, which is basically a characteristic of the modeling that you introduce. So in that sense, it is basically an intrinsic field, not of the beam as a whole, but of the beam cross-section. Now, the average warping vanishes is what one of the constraints, or one set of constraints, 3 out of the 4 constraints basically that we introduced in the end of last class told us. And what that also means equivalently is that the average cross-section is planar, okay? Because warping is what is over and above the rigid body like translations and rotations. So if that the average of that over the entire cross-section vanishes, it obviously means that if you average out the cross-sectional shape, which is indeed a shell, then that average would be planar. Now the base vectors are independent of the choice of the coordinate system's origin. Okay, so this is another important aspect, where irrespective of how you choose this reference line small r in the undeformed configuration, we have been giving quite a few examples of how it could be chosen. One common example of choice is basically the loci of centroids, and we will soon see what is the advantage of choosing it as the loci of centroids, but that is just one choice, and it could be any other choices, loci of shear centers, loci of corners of a rectangular cross section, etc., or for a circular cross section its center, whatever. But irrespective of how we choose that, the base vectors are independent of the choice of the coordinate system's origin. That is, where you put the origin is also equivalently how you choose the reference curve, because the reference curve intersects the reference cross section at basically the origin, where we start with x2 and x3 equal to 0, and then you introduce the small b2 and b3 tangential to the x2 and x3 directions. So that choice of the origin, or how you choose as what loci of what, it is not indicating how the base vectors are there. So in other words, what that implies is that the measure numbers and the constraints of warping are the same. That is, whether you choose this as the loci of centroids or loci of shear centers, what you would have would be the same, and also the corresponding measure numbers would be the same, okay, irrespective of where that origin within the cross section is. And the same holds not only for the translational constraints of the warping, but the rotational constraint as well. Now, imposing the constraints on the warping field implies that the 1D variables are automatically defined. So the way you impose the constraints, I mentioned in the previous class, is not sacrosanct. There are alternate ways of saying these things. That is, the constraints need not necessarily be these four. You could have it in some other way. One alternative we've discussed, probably not with the entire group, but with a large subset of you, is instead of x2 times w3 minus x3 times w2, is to have w2 comma 3 minus w3 comma 2 averaged out equal to 0. So basically that is a more clear definition of the rotation that takes place within the cross section about the x1 direction, because w2 comma 3 and w3 comma 2 both contribute to rotations of the cross section with the appropriate signs, of course, and therefore both put together when averaged out over the cross section give how much of twist basically has happened, and that could be an alternate constraint. So similarly, there could be many other possibilities, but once you have imposed the constraints, remember that the reason why first of all we are having the constraints is the redundancy we had. Instead of 3 variables to describe r hat, we have 7 variables, and therefore we need 4 constraints to take care of that. So once the constraints are introduced, obviously it gives a meaning to the remaining variables that are there. The constraints are on the warping, but the 1D displacement field gets defined, what is its nature because of that, okay? And small variations like using, for example, w2 comma 3 minus w3 comma 2 within angular brackets equal to 0 instead of this will give us very slight change in meaning to some of these u's that are basically involved, or the thetas that are involved. So that has to be kept in mind. But in any case, what is of eventual interest to us is neither this W nor U, but basically this big U, the 3D field, and eventually the 3D strain field and the 3D stress field. Those are the critical things, and those are again immune to how you introduce the constraint. So these are intermediate results which are to be stitched together. Those two parts will be different depending upon how you introduce the constraints. And so it is typically according to our convenience that we have to introduce it, but make sure that once you have introduced the constraints, and also the fact that the orthogonality has to be established, okay? So in other words, what is basically being collected through U should not be collected through W, and what is collected through W should not be collected through U. So this kind of orthogonality between them has to be maintained. And in fact, that was one of the ways, as you saw, how we introduce these constraints by talking about a W which is unacceptable and then making the acceptable W orthogonal to it using the kernel matrix. So next, let's recollect some of the equations that we had so that we can now establish this relationship having looked at these three properties of the warping measures or the warping vector itself. So first of all, you have this 1D displacement vector, small u. It's a function only of x1, and it is just given by the difference in the position vectors of points on the reference curve in the deformed configuration and the undeformed configuration. Once again, I'm continuing to use the color coding, that the deformed configuration, everything is in red, the undeformed configuration in light green, and what is the change between them is basically in yellow. So coming to the three-dimensional case, again the displacement vector. So it is a function of all three spatial coordinates, and it is a difference instead of big R minus small r, it is basically big R hat and the small r hat. It is the difference between them which basically contributes to your big U or the three-dimensional field. Now, using the expressions that we have already generated for big R hat and small r hat in the general case for the beam, in terms of the big R and small r, we can basically establish this relationship that we intend to introduce, and then we will take advantage of these constraints in the warping and see what is basically happening in terms of physical understanding of the relationship between these two. So let's recollect that we got R hat when we introduced the big T system, such that T1 was tangential to the reference curve instead of the big B system. There was one way of writing R hat, so we will choose that. So it could be the other choice as well. So accordingly, you will see a different meaning for W and therefore for small u as well. So your big R hat is given by R itself, except that on the from that point you have to basically go along x2 and x3 in the big T direction, and w1, w2, w3 along the big T direction, because you have actually transformed it or pulled it back from the deformed configuration to the undeformed configuration. So similarly, your small r hat is just r plus x alpha b alpha. All that we will do is we'll subtract these two and integrate. When we subtract these two, big R hat minus small r hat will just become this big U according to this equation, and your big R minus small r on the right hand side would just become U. So all that we have to take into consideration are the remaining terms. So x alpha times here T alpha and here small b alpha. So you can take out x alpha common, and so it becomes just T alpha minus small b alpha, and then you have the warping as well. And then we would like to integrate over the cross section, and when we integrate over the cross section, we can take out of the integration anything which is a function only of x1. Only the things which are functions of x2 or x3 or both will need to be remaining inside the integration. And once again, we will use this notation for integration over the cross section as just angular brackets. So when we do that, we see that this is what basically happens. So again, you have u, and when you integrate small u is a function only of x1. So basically, when you integrate u, it will just become u times the area, because you are integrating over the area. So that we will write as within angular brackets 1. So it's quite obvious, if you integrate 1 dx2 dx3 over the cross section, all that you end up is with the area of the cross section. So this is a notation we use for the area of the cross section. Next, coming to T alpha and B alpha, you know that these are functions only of x1, so they come out of the angular bracket, and x2 and x3 alone remain within the angular bracket. Again, big T comes, Ti comes out, and Wi is a three-dimensional field. Not only does it depend on x1, but it also depends on x2 and x3, and therefore it needs to remain within the angular brackets. Now, it's a very interesting relationship that we see here. One, of course, is the reference cross-sectional area, which is basically what we see over here. Now, our whole goal in this slide is to establish a relationship between the small u and big U. Already we are seeing that relationship getting established over here, but we still need to discuss these two terms that we have. Now, from the way we have introduced the constraints, which is one of the ways of introducing the constraints, we have this average of Wi, or in other words, integral over the cross section, is equal to 0, which basically means that this last term can be left out. Now, if you look at the integration of x alpha, there is a particular point on the cross section which is defined such that the integration of x alpha is equal to 0, which is nothing but the centroid of the cross section. So, If you choose the reference curve so as the loci of the centroids, in that case this term would vanish as well. This has already vanished because of the specific choice of Wi. In addition, the choice of the reference curve as the loci of centroids, for example, can basically set this equal to 0. Then this becomes a very interesting relationship. U is equal to U times the area, or you can take the area down to the left hand side. So small u becomes just the integral of big U over the area divided by the area, which means the average of your big U. So that is expected that the average of the 3D displacement field is nothing but your 1D displacement field. But it has to be remembered that this direct relationship or exact relationship between these two is only under this special circumstance of Wi equal to 0, average of Wi equal to 0 and the average of x alpha equal to 0, so that you have chosen the centroidal axis as basically the reference curve. But of course there can be many other situations, combinations that you can form, that basically the sum is equal to 0, so that basically holds. But in all other situations where this sum doesn't go to 0, there will be a slight difference between the average of big U and what small u is, and that has to be accounted for. But as I said, all of this really doesn't matter if your calculation becomes simpler by the assumption of some other way of introducing the constraints and some other choice of the reference curve instead of the centroidal axis. Go for it. Just that you have to not make too much of the intermediate results. They may not have direct physical relevance, but your eventual 3D results would be acceptable as particularly accurate. So this is basically what it is. So u is equal to u divided by 1 minus x alpha average into t alpha minus b alpha times 1. So again, another interesting situation is, irrespective of whether it is a centroidal axis or not, in case there is no rotation, for example, in a particular problem, let's say it's just a pure extension and it's made out of a material or a material system such that it doesn't introduce any twist or bending coupling with the extension, then you would see that this would be 0. So your T alpha and B alpha would coincide. So irrespective of the choice of the reference curve as the centroidal axis or not, you could still get rid of this term and still have the same relationship between the 1D and 3D displacement fields.
So could you repeat the last sentence?
Yeah. So I said there is a situation. One is the average warping equal to 0 and the average of x alpha equal to 0, which is the centroidal axis. In that case, you have this relationship that small u is u divided big U averaged out, right, over the cross section. There is another situation where you could have this direct relationship, physical relationship between big U and small u, even when you do not choose the reference axis as centroidal axis, if there were no rotations involved in the cross section. That's basically, in that situation, there will be no rigid body like rotations, and therefore your big T alpha would coincide with the small b alpha, and therefore this T alpha minus b alpha would go to 0, and irrespective of whether this is 0 or not, this direct relationship would hold. But even in this case, of course, you require this particular form of the constraint, okay? Because otherwise this term would exist as a difference between these two terms.
That, I mean, the loading is such that T alpha minus B alpha is 0.
Exactly. Of course, one is the loading has to be like that. The other is that the material, because we are talking about composite beams here, there should be no extension bending coupling or extension torsion coupling, because otherwise an extensional load, whereas in an isotropic situation, for example, could result only in an extension and of course the Poisson effects. In a composite, it could introduce bending and torsion as well, because of which this may no longer hold good, because your T alpha can become different from the small b alpha. Okay, so with this we'll conclude our discussion of the beam kinematics. This was very critical and really required the kind of time we spent on it, because this becomes the foundation or basis on which the rest of the theory is developed. And once this is very clearly understood, the terminology behind it is very clearly understood and appreciated, then the rest becomes quite direct and simple to apply, as we shall see in the rest of today's class, as well as in next week as well. So the beam kinematics, again, one reason it is important is basically because you can make the reference curve behavior exact, because geometrically exact theories are available for the 1D. That is one aspect. The other aspect is, by the very nature of the beam, that its cross-sectional dimension is small compared to the length, means that large nonlinear kinematics is possible, or in other words, geometrical nonlinearity becomes important to consider even in class R beams. There, of course, you don't have cross-sectional nonlinearities, but the nonlinearities associated with the one-dimensional deformation still are very large and things which cannot be ignored, and therefore the understanding of the kinematics of the beam, the 1D kinematics as well as the 3D kinematics, and the relationship between them is critical in understanding beams. So the previous slide we saw this, it's just things that I already discussed, but let's just conclude. Reference line choice means that the average of x alpha, or the integration of the cross-sectional area of the x alphas are affected, and therefore the choice of the 1D variables is also affected by the choice of small r, that is the reference line. So then I already mentioned this, cross-sectional centroid loci chosen as r, then you have this equal to 0, and this is what we concluded in the previous slide. 1D variables are defined as average values of the corresponding 3D displacement. So that is basically a linguistic interpretation of this mathematical equation. Then with this we have completed the entire three-dimensional description of beam kinematics, and this is not something the only way you have to do it, but we have looked at a way we can do it, and we have looked at various alternatives which are available to the mathematical modeler, depending upon what he or she is looking for, and those changes can be made. For example, the choice of either the big B system or the big T system on the one hand, the choice of what constraints on the warping to incorporate, the choice of the reference curve. So there are so many things that you still have a lot of freedom over, and within that framework, with all of that freedom, we have established a general kinematics for the beam 3D as well as 1D. Now the 3D beam kinematics, of course, will be useful only if the WIs can be determined. So that becomes the catching point where we are still stuck up as far as our understanding of beam theory in this course is concerned. So we still need to determine WI. We don't know how to determine the WI. As far as the one-dimensional quantities are concerned, which is the rigid body-like translations and rotations of each cross-section, that can be determined by typical 1D codes, and the geometrically exact beam theories for that have been established over a very long period of time, relatively speaking, at least about two or three decades. That has been established, so that we know how to determine. But if at all the 3D beam kinematics has to be useful, and if at all we are wanting to appropriately go back from the 1D model to the 3D model and understand what is happening overall at each material point, and therefore where failure, if at all, originates, where does it originate, how does it propagate, etc. If we want to have a better understanding of all of those, then we definitely need to determine warping, because that is the connect, as we saw in the previous slide also, between the 3D and the 1D field. So once the warping can be determined, you can always go back and re-establish the connection and recover all of your 3D fields. So how do we go about it? Of course, WI is a set of three field variables, the out of plane measure number and the two in plane measure numbers. And then they are, of course, functions, because they are three-dimensional fields, they are functions of x1, x2, x3, and in a dynamics problem, time can come into picture as well. And specifically when you are looking at high frequency dynamics, then time plays a much more critical role. So how do we go about doing that? That's where the variational asymptotic method comes in. we will be applying the variational asymptotic method, and we will see how that in turn enables us to determine the W's. But in order to be able to apply VAM, we have to understand what VAM is, and that's basically what we will do next. So what we intend to do here, of course, is to apply VAM for beam cross-sectional analysis. That's where the warping can be determined, because warping, remember, is a function of x1, x2 and x3, but it has to be explicitly determined in terms of x2 and x3 and implicitly determined in terms of x1 through the 1D measures that we have already introduced. Remember, we have introduced the one-dimensional strain as having 4 components in the simplest general beam model, which is basically gamma 1 bar, kappa 1 bar, kappa 2 bar and kappa 3 bar, the extensional strain of the reference curve, the twist per unit length plus the torsion of the curve, and then the 2 bending curvatures. So now that relationship is basically has to be utilized here. Now what we are trying to see is how we can apply the variation asymptotic method to the beam cross-section analysis to determine those W's and therefore the all of the 3D fields. But even before we do that, in the next slide, what we will do is to introduce VAM as a mathematical concept and see how it can be used as a tool in this particular problem. So what are the goals here? The first goal, of course, is to describe VAM briefly, which is what we'll do in the next couple of slides. Once we are done with an overall understanding of VAM in terms of the mathematics involved, then we will illustrate VAM through an example which is a non-structural example. We'll just take an arbitrary functional and see how, when VAM is applied, those procedural details that we describe over here, how they are incorporated into that example, and then we will get on to a structures problem. So we will reduce the 3D kinematical description that we have gone through in the last few classes into the one-dimensional beam model, which is the reduced order model, because from 3D you're coming to 1D, that's why it's called the reduced order or dimensionally reduced model. Next, what we will do is to develop, based on the VAM application to the cross-sectional problem, we will develop 2 types of asymptotically correct beam models, and this is again within the same framework. One follows the other. It's not like 2 separate problems, but through the same problem we are establishing at 2 different levels 2 types of beam models. One is basically the so-called classical beam model, and the other is the refined. The classical would not capture the transverse shear effects, for example, in a class R beam, whereas the refined would be able to, but in an indirect fashion, because it would not introduce the 2 gamma 1 2 and 2 gamma 1 3 explicitly, but it would be contained within the warping. So in that sense, it is a refined beam model over this, and when you recover the 3D fields, they would behave as they would if the transverse shear were taken into account. But you would see that in the entire modeling process, the transverse shear variables are not explicitly introduced anywhere. So that is the refined model. One disadvantage of that is that you cannot compare it with existing models in the literature, especially Timoshenko-like models, because you don't have gamma 1 to gamma 1 3 explicitly appearing, but you would be able to compare. If those models gave you the 3D results, then you would be able to compare across them. But the intermediate results at the 1D level for transverse shear in particular, you will not be able to compare. There is another disadvantage with using this model as it is that it involves the derivatives of the 1D strain. So not only does it involve the strain energy in terms of gamma 1 bar and the kappa I bars, but it involves some derivatives with respect to x1 of those as well, and which means that when you eventually do the one-dimensional analysis of the reference curve, there will be additional boundary conditions which are involved, and some cases they may not be physically intuitive the way we approach the beam problems typically. So, but there are ways to overcome that, and you could still do that. But because a lot of people prefer to compare with the Timoshenko-like models, what we will do is to force this refined model to behave like a Timoshenko model. And when we do that, we observe that it is not exact. Whatever result we get out of that will not be exact, because of the fact that unlike Euler-Bernoulli beam theory, which is asymptotically correct theory, the Timoshenko beam theory is not an asymptotically correct theory. Okay, so there are errors in it, though it works for a good number of engineering problems and therefore rightfully used in a lot of engineering applications, but it is mathematically proven rigorously that it is not an asymptotically correct theory, and therefore when we force this so-called refined theory, both of these are asymptotically correct at different levels. This is a zeroth order approximation, first order approximation. This as it is can be compared with an Euler-Bernoulli beam theory results, for example. But if you want to compare this, you have to bring 2 gamma 1 2 and 2 gamma 1 3 into the picture, and when you try to do that, what happens is basically you introduce certain errors, and you have to live with that. You can mathematically minimize those errors, but you cannot set those errors to 0.
So what does this asymptotically correctness imply here?
Yeah, in all places, whenever we mention asymptotical correctness, basically it means that if suppose an exact solution were available for this problem, and we get an approximate solution either through VAM or through some other means, we want to compare these two solutions, the exact solution and the approximate solution. Now, if we expand out the approximate solution in powers of the small parameters which are natural to the problem, both these solutions should agree with each other. Okay? But if they don't agree, then we call it asymptotically incorrect. So in this specific case, the small parameter of primary concern is the cross-sectional dimension divided by the length. So as this cross-sectional dimension divided by length tends to 0, the exact solution and the approximate solution should match. Then it is said to be asymptotically correct. If it doesn't, it is not asymptotically correct. And in that sense, Timoshenko model has been proven to be asymptotically incorrect.
So this refined beam theory, that means we are considering small local rotations, and that is contributing in towards gamma 1 to
No. Even within the small local rotation itself, there is still an asymptotical incorrectness which is involved. For class R beams, for all types of loading, the small local rotations are indeed small. Okay. Otherwise, what they do is, if they are not small, they make the strains large and therefore the material to fail. So, when you come to class P and class S beams, there is something over and beyond this refinement. This refinement that I am talking about is specifically for class R beams, where the transverse shear comes into picture. There is a level of refinement to bring in the nonlinearities in the case of the class T and class S beams, like the trapeze effect, brazier effect, etc. That is,
those are not included in this.
That is not included in this. Okay. But of course, when upfront you are starting to apply this method to let's say a class T or class S beam, it will show that, for example, in a class S beam, the transverse shear strain is not a very important contributor to the energy. So instead of that, you would get the nonlinear terms coming into picture rather. So when you're going from the zeroth order approximation to the next higher order approximation, instead of getting this, you would end up getting the nonlinear terms, which are more important than the transverse shear's contribution to the energy.
So we can use the B coordinate, capital B coordinate system, which will give the refined theory with the transverse shear strains.
That's correct.
Why should we go for the T and then
so then you basically have 6 different strains to start with, but as I shall show in the variation asymptotic method itself, one utility is of course to get dimensionally reduced models, but the variation asymptotic method can also be used to determine the degrees of freedom of a particular system. Okay, in this case a beam system, and there it very clearly shows that there are only actually 4 degrees of freedom that exist. Okay, and those are contained within the gamma 1 1 bar and the kappa I bars. So when we are introducing 2 gamma 1 2 and 2 gamma 1 3, we are doing it in a artificial manner. It's nothing wrong. Just like we are introducing, instead of 3 variables, 7 variables, we are introducing 9 variables or 9 variables. So that's basically has to be appropriately tackled and brought about. So that is definitely one way to approach the problem. There are issues in terms of the mathematical handling there as well, different from the mathematical issues involved here, but it's definitely an alternate acceptable process. So when we want a Timoshenko-like model, what we can do is we transform that refined theory into a common engineering model, and that, as I said, involves trying to, in an analytical way, minimize the error between the asymptotically correct refined theory and the asymptotically incorrect Timoshenko-like model. So that's when you end up with a Timoshenko-like model. It's not exactly the same as Timoshenko's model, but it has a form similar to the Timoshenko model, so that you can have a one-to-one direct comparison, not only at the 3D level but also at the 1D level. And another goal here would be to derive the recovery relation, and this is actually a byproduct of this determination of warping. So it's not something that we have to do separately from determining, let's say, the cross-sectional stiffness matrix, for example. To determine that, anyway we have to determine the warping, and therefore those warping, which are basically a three-dimensional field, eventually help us to get the three-dimensional total displacement field, and then the 3D strains and the 3D stresses as well. So all of those recovery relations are also obtained as part of this variational asymptotic method process. Next, we relate the refined theory to the so-called generalized Vlasov approximation for class T beams. So probably we'll not have time to get into this in this course, but those of you who are interested can look at those aspects which are covered in detail in the book. And then also obtain the trapeze corrections asymptotically. Again, this can be done in two different ways. One is using a numerical approach using finite element analysis, other is by using a analytical closed form solution approach for class S beams, as well as a large number of class T beams as well. So those are covered again in your book, but we unfortunately do not have time to touch upon the details of those derivations. But all of you, including those who are not part of our lab, are always welcome, even beyond the course, to come and discuss with me, especially if these things involve something that you're researching towards, to discuss these aspects also with me whenever you need me. So with that, we will start the introduction to the variational asymptotic method. And again, I will introduce a specific color pattern here for pedagogic purposes, so that we have an understanding of things in a better manner. So I use three colors: red, blue and yellow. The yellow will refer to the small parameters. So wherever small parameters are used, either in a sentence or as variables within an equation, I'll try to use yellow color for that. And then the stationary points or the solutions that we are looking for, either the exact solutions or the approximate solution, or as a part of a set that in which the solution is contained within. So for those I'll use basically the red. And how do we get those stationary points of what? That basically it could be the strain energy, for example, whatever is the functional, that whose stationary points we are trying to get. In our case, of course, most cases it would be minimum, but irrespective of that, we are only interested in the first variation being set to equal to 0, and therefore we are talking about the stationary points. So those functionals like energy, we will represent with a blue color. So what is WAM? WAM is basically a mathematical technique. It is not something which is specific or peculiar to beam problem or shell problem or any structures problem for that matter, but for a whole range of physics problems where you can have a variational formulation for the problem itself. The problem has to be defined in a variational form, and then you should be able to identify within the problem definition some small parameters so that you can apply the asymptotes in the functional with respect to those small parameters. So that is basically the idea, and of course it is useful only in places where you cannot find an exact solution for the functional. So if you can find the stationary point of the functional even without taking advantage of the small parameters easily, well and good, you can directly do that. There can be nothing better than that. But in most engineering problems, the functional is so complicated that determining the stationary points exactly either is not analytically possible, or when numerically possible is computationally involved and takes too much of computational time and effort, and therefore in most of such situations it makes sense to take advantage of small parameters which are anyway there within the problem definition. It's not something that you are making an assumption or approximation beyond the problem definition. It is there in the problem itself, so why not take advantage of that and determine instead of the exact stationary points of the functional, approximate stationary points of the functional. And in doing that, we will also introduce certain concepts of approximate values of this functional to determine the approximate stationary points of the original functional. So that's something we will evolve as I describe this method to you. So as I said, it is applicable to any problem. It's been applied for some fluid mechanics turbulence problems as well. To any problem seeking stationary points of functional with some inherently small parameters. It's appropriate tool to build, of course, from our end. This is the main purpose that we are introducing it. This is what we will use it for in this course, to build accurate models for dimensionally reducible structures, by which we mean that within the overall dimensions of the structure, it is possible to identify certain dimensions which are of different order of magnitude compared to other dimensions of the same structure. So either small or large, and therefore the appropriate ratios when in the case of the large ratios, when you take the reciprocal, it becomes a small ratio. So the elasticity problem is restated in a variational form, and this is something which is done much before the VAM came into picture. So there have been variational approaches for structures problems, in particular the elasticity problem, where it is stated as obtaining the stationary point for the energy functional that would lead you to solving the elasticity problem. And most of us know from the exposure to theory of elasticity, there are a whole class of problems within the theory of elasticity for which solutions are not possible in closed form analytical sense, and where numerical solutions are possible, it is computationally highly involved, and that's the reason why 3D finite element analysis of most structures takes enormous amount of time, CPU time.
So, but generally, as you said, that it has been applied for fluid dynamics problem as well, turbulence cases and all. But in those cases, generally you do not encounter energy functional as we...
Exactly. So you will have to make certain modifications based on certain approximate theories for those problems as well.
But we can always construct some kind of weak form.
Exactly.
So can that also be a starting point of...
Definitely. So next is the small geometric parameters. The first is the existence of the functional. The next, and whose stationary points need to be determined. The second aspect is the existence of small parameters. In the specific problem that we are interested in, dimensionally reducible structures, the small parameters happen to be the geometric parameters, apart from the physical parameter of maximum strain itself. And small geometrical parameters are there in beams and shells, and we already in the first few classes we looked at the reasons why beams and shells are so extensively used in engineering structures in general and aerospace structures in particular, and therefore the analysis of them as they being primary structures becomes critical, and the existence of small parameters in both of these kinds of structures makes it attractive for us to apply the VAM there. So what we will do in today's class is to introduce certain basic notions of VAM, and for details, if those of you are interested in getting into much more detail on that, there are a lot of references in your textbook, but specifically if you're looking at shell analysis, for example, then how VAM is applied to shell problems. There are of course a lot of things which have evolved since then. But the first and foremost work on this was by the person who introduced VAM itself, and done quite some time back. So there are papers related to that, and he has a book as well in which many of these papers are well summarized. And then of course the group of Hodges at Georgia Tech has basically taken this further in terms of how it would be more directly applicable for engineering problems. Then again, for the class of beams, once again Berditchevsky himself has applied it to a class of beams, and later on there is a German researcher who also applied it to beam problems. And then of course once again you have a very large range of papers by the group of Georgia Tech who have worked on this. So next, so that's as far as the literary description of what the method does is concerned. We'll follow the same color coding that I introduced in the previous slide, but now get into the mathematical aspects of it. So first of all, there has to be a functional, and this functional is in blue, and it depends on a certain set of elements, let's say of functions. It could be vectors, vector space, but basically these are like dependent variables. So functional, you can in a loose sense think of it as a function of functions, which serves for, at least for the purposes that we are talking about here. But basically it's mapping a vector field to a scalar field, so that is the primary purpose here. But this functional, different from a general sense of a function, in our specific case we are interested in the subclass of functionals where a small parameter can be identified within the functional definition itself. So for example, this could be the strain energy of the beam, and the strain energy would depend on the three-dimensional displacement field of the beam. And within the strain energy, because the strain energy has to be integrated over the entire beam, so obviously the cross-sectional dimensions and the length would come into picture in your integrations, and within the integrand itself, in terms of these strains, how they depend on derivatives with respect to various spatial directions, and therefore the orders of magnitude of those spatial directions. So through all of that, these small parameters will come into picture. So this functional depends, depending on small parameter A. It could be a large number of small parameters or just a single small parameter. The description that we will do will be general. It could take into account either one of these situations. Again, U itself could be just a single quantity, or it could be multiple quantities. Like in our case, for example, it could be the three-dimensional displacement field involving U1, U2 and U3 in the three different directions. But what we will talk about now is in a more generic sense as a mathematical procedure. Okay, so it's defined on a particular set M of the elements U. So in our case, for example, if this were the three-dimensional displacement field, this would be the acceptable set of displacements which will be acceptable for the for being utilized in the energy function. So that is what we call that set as a whole as M. And it could so happen when we are going from the 3D to the 1D problem, this set M in the first instance could turn out to be the so-called rigid body-like translations and rotations, and then eventually bring in the 3D aspect. So we'll see that as we go through. But right now we have a functional, we have a small parameter, and we have the dependent variables that we want to determine the solution for. So this U in turn depends on the independent variables x1, x2, x3 and time in general. In a general mathematical problem, it could be an n-dimensional independent variable set that it depends upon. Next, what is the goal that we want to achieve by applying VAM? We want to obtain, instead of the exact solution, which is either impossible or difficult, therefore we want to obtain approximate stationary points instead of the exact stationary points. And these approximate quantities I try to indicate by black. I hope I have done it consistently. But basically approximate stationary points of I of u comma a, and that is to be achieved by using this method that we want to introduce through this description. So to do that, before getting to the approximate stationary point, that is u, what are approximate values of u, instead of I, we are now introducing a different functional, and that we will call as I subscript 0 or I naught. So this functional is constructed using the original functional I of u comma a by just taking only the leading order terms with respect to those small parameters. So there could be terms which do not depend on a at all, for example. So and those could become the leading order terms. Then there could be terms which depend, which are proportional to a, then terms which are proportional to a squared, etc. In some problems, it's also possible that there are some terms within the function which are dependent on the negative powers of a. So then obviously they become the leading order terms even before the terms which are independent of a come into picture. So that is quite obvious and something which has to be taken care of. Right, so we construct this new functional I naught by neglecting all the small terms, or in other words, dropping off the higher order terms with respect to a. So in an asymptotic sense, with in the original function.
So in that case, we can always rescale if higher.
Exactly. Yeah. Yeah. Definitely. So denote m naught as a different set from this m that you already had as a set of stationary points of I naught, u comma a, because it is possible that when you try to determine the stationary points of this new functional, it may not give you a unique solution. Even if the original functional, let us say, had a unique stationary point, it is possible because of the way we are constructing this functional, by dropping off the higher order terms, retaining only the leading terms, it is possible that this may not have a unique solution. So let's first take that situation into account. Of course, if it does have a unique solution, a lot of these steps will be redundant, not necessary, and directly we'll go to the next step, which we shall discuss probably in the next slide. So, in the case where we don't have a unique solution, all of those we club together and we call it a set M naught. It's a set of stationary points of I naught of u comma a. So now, a special case is when M naught has a single element, that is basically, in other words, it's unique. Then, so that is also included within the description here. So it becomes the first approximation to the first stationary point of your original functional. It is an actual stationary point of this, but it becomes an approximate stationary point of this particular function. Again, there are certain mathematical proofs which go into the rigor of this and try to show that indeed is the case. We will not go into those aspects. Our only goal here is to apply this method to that to this problem at hand. So we will not go into those detailed mathematical proof aspects in the course.
So like by stationary point,
Yeah.
like the way you are obtaining the stationary point is taking the first variation on
Exactly, and set it to 0. So usual process that's involved in calculus of variations.
So, like in case,
Yeah.
like say for suppose we get a linear differential equation second order, so
Uh-huh.
we will have two such solutions.
Mhm.
Like so, in that case, by like so you want to refer to M as the set of solutions for that kind.
M naught, yeah, right. So in the case of the beam problem, what this would be, for example, is that when you're trying to minimize the energy, you would get a solution for the warping explicitly in terms of x2 and x3, but not in terms of x1. So in that sense, it is still undetermined in terms of x1 through your gamma 1 bar, kappa 1 bar, kappa 2 bar, kappa 3 bar. So that would become constitute the set M naught, because those quantities are not yet determined. So in that sense, there is a non-uniqueness still left, that these quantities can take a wide range of values, of course maintaining small strain, but a wide range of values, and still the solutions would be acceptable as far as this level is concerned. So that's where this kind of issue would involve. Another thing is, of course, when you do not bring about the decomposition the way we have done, let us say by introducing those 4 variables, 1D variables and 3 warpings. Suppose we directly start with a 3-dimensional description and go for minimizing that big U that we were talking about, the 3D displacement field as a function of x1, x2, x3, and when you apply this method and take advantage of the small parameter, namely cross-sectional dimension divided by length, it will automatically lead you to those 4 degrees of freedom. That is basically the extension, the transverse translations, or equivalently the rotations about those directions, and another rotation associated with the torsion. So that will then constitute that particular M naught. In other words, in some sense, you are extracting the so-called degrees of freedom of the system. Okay, it's used in a loose sense, not in the usual sense that you're talking about the degrees of freedom, because this is an elastic flexible system, so it has infinite degrees of freedom. But basically, in this dimensional reduction process, when you're going from the 3D to the 1D model, how many 1D variables are required? So that, in that sense, those are the degrees of freedom that we're talking about. And if you are applying the VAM in that way, without bringing in the 3D kinematics the way we did, and upfront you're trying to apply the VAM to the 3D problem, then your M naught would constitute those 4 variables associated, let's say U1, U2, U3, the small U1, U2, U3, and theta 1. So these would constitute those degrees of freedom that you would be extracting at this stage as the leading portions of your overall 3D displacement field, that is the big U. So Then, so that is the simplest example where M naught is having a single element, or in other words, you've got a unique stationary point for this, and that itself becomes the first approximation to the stationary point of the original functional. The other case, which is what we will encounter, sometimes the set M naught has multiple elements, even if the original functional itself had a unique stationary point. This is something I mentioned already. Next, what we do is, how do we proceed further in such a situation where it is not unique? We fix any element U naught of M naught. So, for example, when we want to solve the cross-section analysis problem, we are not bothered about how things change with respect to x1. So, we take gamma 1 bar, kappa 2 bar and kappa 3 bar, even though they are functions of x1 as constants, because we are only dealing with a particular cross-section where x1 equal to x1 star. So, it is fixed. Okay. So, in that sense, you can fix any element U naught of M naught. Of course, it has to be within that set, but any one of those elements we are basically fixing, and then representing the displacement field, or for that matter in this case the dependent variable in the more general mathematical problem, as the solution which you already got, of which you have taken a particular one, and then you are adding some perturbation to it. Okay, and it's quite obvious that since you have got the solution at this level for the leading order terms, this one would be smaller compared to this. So in other words, it's a perturbation. So in an asymptotic sense, your U1 has to be small compared to U1 has to be small compared to U naught. Otherwise, what it means is that you have not got the actual solution already. So that is basically your U naught would be spurious. So in case U naught has been obtained properly, it's quite obvious that U1 will not replicate those orders of magnitude. It will only contribute higher orders of magnitude. So therefore U1 is smaller compared to U naught.
Sir,
Yeah.
when you say M naught has multiple elements, by that you mean that the 1D strain measures are still undetermined, and hence they can take any arbitrary functional form.
That's correct. Yeah.
And when you say that it is uniquely determined, that means U naught is explicitly determined in terms of all three field variables, x1, x2 and x3.
That's correct. Yeah. Yeah.
Okay, that means in that case we directly go from the functional to the final solution rather than going to the 1D and then...
No. In that sense, you are not anymore extracting the degrees of freedom, but still you will have the option to improve your solution by, because remember this, what we are talking about is only I naught, by taking the next higher order terms in I, etc., to improve the solution. So you would still have that opportunity to do that. But the fact that M naught has been entirely determined, or no longer you have further things to be determined, basically means that you are not going to add any more degrees of freedom, but those degrees of freedom which you have already obtained, you are trying to refine further for better solutions.
So how do we obtain degrees of freedom here? It was clear.
See, again, degrees of freedom is used within course, just like we talk about rigid body motion. That's again a rigid body like motion that we're talking about. So it's used in a loose sense to look at the analogy between how you talk about typically the degrees of freedom of, let's say, a non-flexible system. So in this case, what we are talking about is the VAM has decomposed your 3D problem into two parts: the cross-sectional analysis and the 1D analysis. So in the cross-sectional analysis, when you're doing it, there is certain things which are coming from the 1D analysis, which are your gamma 1 bar, kappa 1 bar, kappa 2, kappa 3 bar. So that is basically the four quantities which we are calling as the degrees of freedom in this sense. In a general mathematical problem, the way we are describing it here, it means that this I naught does not have unique solution. Whether or not I has a unique solution. It is possible that I naught doesn't have unique solutions, and in such situation we club all those solutions together and call that as M naught, or the so-called degrees of freedom. Yeah. So that's what we did. We fixed one of the elements of M naught. We call that as U naught, and then we perturbed it by a quantity which is smaller than itself, and then we go ahead and substitute this new value for U into the original functional that we have here. So here that U becomes U naught plus U1. Still, of course, the small parameters are there, identifiable within the definition of the functional. Again, we want leading terms. But this time it's obvious that because u0 is bigger than u1, the leading terms of this directly, if you look at it only in terms of size, obviously they are the things which purely involve u0. They are things which do not involve u1. We are not interested in those terms because next goal is to determine u1 so that we have a better approximation for the original u. Okay, so that is which is the original stationary points of the original functional. So that is what we intend to do. All that we want to do next is to determine this u1. So what we will do is not talk about the leading terms of I itself, but leading terms of I which involve u1. So some of them might involve a combination of u0 and u1. Some of them might involve u1 alone without interacting with u0 in those terms. So all of those terms which are the leading order, we will now club together, and those are the subset of that, and we will then form a new functional I1 which is depending on u0, depending on u1 and depending on a. But none of the terms in that are purely dependent on u0. Even if they are there, it doesn't matter because we are going to take the variation of this, and those terms would anyway variation with respect to u1, and therefore those terms will anyway drop because u0 has been determined. So which means that the variation of those terms would anyway drop. So, but just for compactness of what you do, it's convenient if you just leave out all of those terms and directly deal only with the terms which are involving u1, either as products with u0 in some way or u1 by itself.
So in case like you are not able to solve for u0, like after like going for the first variation of that I0, if we get an equation wherein this u0 is not explicitly solved for, like differential equation, nature of the differential equation says that like exact solution doesn't exist.
See, at this stage, it is just the identification of u0 which is important. Once the identification of u0 is done, your u1s will be determined in terms of u0. Okay, so everything gets determined in terms of the u0. Then you have a separate problem where you have to solve for the u0s. Okay, so in our case, for example, those u0s happen to be the 1D variables. So what would happen is the warpings would then be determined in terms of these u1s could be, for example, the warpings. So they would be determined as in terms of the 1D variables, gamma 1 bar and kappa bar. But everything would get stuck up if you continue with this in terms of those that set of m0 or the u0 that you have chosen there. If you want to determine that, then you have to probe back into the 1D analysis of the beam. So that is basically where you get a solution for the problem. But basically that problem becomes much simpler than the original 3D problem that you wanted to tackle. So similarly, in a general mathematical sense also, you would have a different problem definition in terms of those u0, and then you directly go and determine that u0. For both the determination of u0 and the other perturbations, the overriding factor is this problem definition. That is, you have to find the stationary points of this functional. So you are doing that in steps now. One is determining all these u1, u2, u3, etc. in terms of the u0. That is solved. So now you are left only with the u0s, and then again you are basically minimizing the functional to determine the u0s.
You know, actually what I wanted to say is that like this stationary point of functional means like it will be some kind of a function expression.
Exactly, right.
So like, but it will come to like that functional stationary point of the functional, like solving for the stationary point of the functional means you have to finally solve some differential equation.
Correct.
So what if this the solution of the differential equation doesn't exist? Doesn't exist in the sense we cannot get a closed form solution.
Then you have to go for an analytical, numerical solution. So that is the only way. Even then, you would still have a computational efficiency because the differential equations that you are solving would be less complex than the differential equations governing the exact solution of the original function.
And symbolically, you can always treat this like we can, like as you said that that I1, which involves at that level, we can always think that we have solved for u0. So like when you take variation with respect to u1, then we
exactly.
At that level, we can always go about doing that explanation. But still, like when it comes to explicit solution, then there will be a problem.
No, because
we can fall back to this numerical method.
See, in this case, the differential equation governing u1 would involve certain independent variables which are there only in U0 and not there in this.
Yeah,
So in that sense,
the
the derivatives
equation involving U1 will have parameters of U0.
exactly.
But that actually will be, say, some kind of functions, like we have differential equation with time varying coefficients.
Right.
Like that we will have.
Right. So as you said, we can do that in a symbolic sense. Okay. And so in the beam example for that, you would determine, let's say, the warpings explicitly as functions of x2 and x3. Okay. So you will know the functional form in terms of x2 and x3, but you will not know the functional form in terms of x1. It will be through the 1D strain variables. Okay, so we have already formed this new functional with the leading order terms consisting of the perturbation U1 to U0, and then we again check the first variation of I1, set it equal to 0, and then try, so in that process we try to determine the stationary points by which we make the solutions for U1, which set delta I1 equal to 0. So then U1 is determined. It's quite obvious that those U1s in general will be a function of the U0, and it is determined. Of course, it will also have certain small parameters. So you can basically look at each term and see the different orders of magnitude of the solutions as well, apart from the functional.
So we are here also we are using that Saint-Venant warping function. Like one is we are considering warping as a product of two things. One as a function of x1 alone, and the other as x2 and x3.
There it was introduced in an ad hoc manner, in the sense that without background to it. Here you start, it is not shown in a lot of papers because it is taken to be understood, but what is actually done is you start applying VAM first to the 3D problem, not to the problem of the beam kinematics that we have developed in this course, where we have already related the 3D to the 1D variables. In other words, we have explicitly brought in the 1D quantities, like either in terms of the gamma bars and kappa bars, or in terms of the small u's and the thetas. Okay, it is not necessary to do that. You can directly apply it to the big U's as a function of x1, x2, x3, the three-dimensional displacement field, and then you would extract out these degrees of freedom. Okay, so if I1 has unique stationary points, and U1 is determined by U0 and A, otherwise the other option is, when it's not determined, the same procedure has to be done over again, so that the degrees of freedom which have not already been extracted into M0, like U0, will then continue to be extracted, and you will reach at some point, and typically it doesn't take more than one or two iterations. In most cases, just the first step itself gives you all this so-called degrees of freedom. It's only in situations where the degrees of freedom themselves are such that some are contributing larger amount to the functional and some are contributing lesser amount to the functional, and still the perturbations are much lesser contributors than that. In such situations, you will obtain the degrees of freedom in steps. Okay. In most situations it does not happen that way, but if it does, then you have to go through this procedure until all the so-called degrees of freedom have been determined using this process. So in our case, of course, the degrees of freedom could be the rigid body translations and rotations, or put in a different way in terms of the 1D generalized strains. So the rule here is that the additional degrees of freedom, you can see, will disappear after a finite number of steps itself, and the solution is determined by some set of elements. Let's call them as U0, U1, etc. Now U1 would be a function of U0, U2 would be a function of U1 and U0, and therefore each one of them eventually can be thought of as function only of U0 only. Okay. So in practice, as I said, above steps needed only if the degrees of freedom are not known a priori. So in situations where, for example, I just described, where you are applying it directly to the 3D problem, where you don't know that there are these 4 degrees of freedom, that was done originally by Berdichevsky, and it's from that point of time that everybody already knew that those are the 4 degrees of freedom, and any refinements that people who are doing, they didn't revisit that original problem. They started off with the kind of 3D beam kinematics that we have introduced, and then try to find the refined solutions. So In practice, the above steps are needed only if the degrees of freedom are not known a priori, but in our case, we know those degrees of freedom a priori and will take advantage of that.
This means that in case of any problem in general physics where it is not known what are the degrees of freedom, the process will itself turn out that these are the determining degrees of freedom for the reduced structure.
That's correct.
And that has been done for the beams, and that's why we always talk about gamma bar and kappa.
Exactly, exactly.
And here U naught is what is referring to all those gamma and kappa.
That's correct, exactly, yeah. Either you can think of that or as the rigid body translations and rotations, which in turn are related to the gamma bar and kappa bar. So, equivalent way of looking at it.
Sir, in that case, like 3D displacement fields does not involve warping as such because they are point-wise fields.
Yeah.
But when we talk about beam, we come up with warping functions and all.
So what would happen is, suppose you apply the variation asymptotic method without introducing 3D beam kinematics, without introducing warping also, right away to the 3D displacement fields, at the so-called phantom step, what we would get is these 4 degrees of freedom. So then, as you saw in the previous slide, we are perturbing those, okay, with U1, etc. Okay, so those U1, for example, could become the warping, okay, which is determined in terms of your gamma bars and the kappa bars.
So will it also come out along with the constraint equations, because unless the constraints are there, there is no definition for the one. There is no physical meaning for the 1D.
No. See, this process, the way you are introducing the additional quantity is a higher order term compared to the previous one. So in a sense, an orthogonality is already built into that. Okay, so in other words, you have already extracted out things of a certain order of magnitude, and then you're going for the next higher order of magnitude contributions. Okay, so that U1 that which is introduced is small compared to your U0. So that automatically takes care.
Sir, what was this Vlasov effects and other
Vlasov effect is the end effect, the dependence of the strain energy on kappa 1 prime.
Yes.
Okay. So basically, one example that we gave, for example, is the die beam with all those forces.
That will come in this.
Basically, end effects, restrained warping, how it contributes to the strain energy, and how the Saint Venant's principle fails sometimes. So these kinds of issues, which are there specifically with class T beams, would be the Vlasov.
In this procedure, if we apply VAM.
Yeah.
So that will come in this U1 portion, right?
Exactly. There are two ways of looking at that U1. One stage is at the previous slide where I was talking about, where the degrees of freedom had not yet been determined.
Yeah,
so then that U1 might also include additional degrees of freedom. Okay, but once all degrees of freedom have been recovered, then whatever addition that you're doing is basically bringing in those refinements like Vlasov in the case of class T, or trapeze in the case of class S and class T, etc.
That will include in U1 terms, U2 terms and other terms. Right?
That's correct, yeah. Right. Okay, so if the degrees of freedom are already known, the problem is formulated based on those degrees of freedom. That is, that's what we are doing in our case. The first approximation yields unique solution without the iterations that we talked about in the previous slide. To construct the refined theory of order epsilon of A. So now we know that A is a small parameter. So let's define some function of that A. This function could be, let's say, A squared or A cube or whatever, something related to A. So, and suppose we want to determine everything up to that particular order. To refine, that determines what level of refinement your theory has. So that's basically the function epsilon of A. Now keep in the function all the terms of that particular order. So that is a direct definition of a refined theory of a particular order, means that in the functional all terms up to that particular order should be kept. So that is how that refined theory is defined. So now next, if we want to apply it to either our beam problem or to the simple example, general example that we are going to give, certain concepts have to be known. Some of you might already be familiar with, but for those of you who are not familiar with, an introduction to these concepts in a very basic sense would make the understanding better. So some of the things that we will look at are the types of functionals classified as linear, bilinear and quadratic functionals, because eventually we will see that the strain energy is a quadratic functional. So what it means mathematically and what are the properties involved, so that we can take advantage of those during this minimization process of the approximate functionals. So first of all, let's say we have some set of real numbers. For all real numbers alpha I and for all elements ui of some set, let us say m. And here when I say ui, we are not talking about some measure numbers or some components of something. It is basically the number of elements within that set m. So it could be u1 through un. Okay. So all of those elements are present within that set m. They are constituting that set. Now, if let's say it has a certain property such that alpha 1, which is a real number, times u1, which is an element, plus alpha 2, which is another real number, plus u2, which is a part of that set, if this sum is also belonging to the same set m, then basically we call that m as a linear space. Okay. So now within this linear space we will introduce a so-called linear functional. So the understanding of linear space is required to understand what is a linear functional. So now suppose there is a functional L of u, then we say that that functional is linear functional if we can break out a functional in this manner. So if you have a functional of u1 times alpha 1 and a function, the same functional of u2 times alpha 2, if you can basically put it together inside, then basically this is a linear functional. So again, similar concepts you would have learned in different situations as well, but we're just introducing this in a formal sense for functionals. Now if we introduce another set of subset within this, let's say VIs, they are again similar elements of M, just that we want to have some kind of a distinction between that artificially to start with. So let's call some of those elements as UIs and some of those elements as let's say VIs. And now if you have these two sets of elements, and of course they could be interchangeable also. Some of the UIs could be VIs and the VIs could be UIs as well. The whole idea is to graduate from a linear functional to a bilinear functional definition. So now let's say there is a bilinear functional, because a functional can have multiple arguments as well. So let's say this functional is dependent on u's and v's. Okay, it could also be written as epsilon of u comma u. Okay, so that is also an example of a bilinear function. So now this particular functional is bilinear functional. It is called bilinear. In a similar kind of a definition to the linear, it's just an extension from a single argument to a double argument. In other words, for example, in the first argument, if you have a linear combination of u1 and u2, you can break it up into a linear combination of the functionals of u1 and u2 in the same way with the same coefficients alpha 1 and alpha 2 you have. And that can be done not only with respect to the first argument, but also with respect to the second argument, as you see here. And of course, in a combination, when you have both the first and the second argument, you will have a much larger number of terms which can be determined in a series of steps, and that is something which will be useful for one of the examples that we will encounter. Now we have a special case of this bilinear function which we will next introduce, the quadratic function, which is basically combining these two functions that we already introduced, the bilinear and the linear functions. In other words, the bilinear functional is actually a subset of the quadratic functionals. Just like in the case of a polynomial, for example, a quadratic polynomial could involve x squared terms, x terms and constant terms. So just x squared alone is what would be an analogy to the bilinear function that we have introduced, whereas the quadratic function will involve this and this as well. Next, we have some specific cases of a bilinear functional. What we call as a symmetric bilinear functional is when you can interchange the two arguments that it has. So e of u comma v will be equal to e of v comma u. Next, we introduced the concept of positive definiteness, which is again something which is directly relevant to the strain energy function that we will have. In fact, we talked about that in one of the first few classes. So, if you have the E of u comma u greater than 0 for all values of u which are not basically non-zero, so in such a situation you call that E as a positive definite bilinear functional. And then if the E of u comma v is symmetric bilinear functional and L of u is a general linear functional, and you have a combination of them but with both the arguments the same over here, and then you define a new functional I of u, then we call such a function as a general quadratic functional. In a special case where L of u equal to 0, which is acceptable, also that is also a quadratic function. This is a more general way in which you can have a quadratic functional. Now we will have a situation where when we expand out the energy, we know that in terms of the 3D strains it is quadratic, but we are introducing the 3D strains in terms of the 1D strains and the warpings. So, and our goal would be eventually, as we will see, to determine the warpings in terms of the 1D strains. So there will be certain terms which are involving, let us say, warping squareds, or rather the warping derivative squareds, and there will be also terms which involve linear or proportional to warping, but it will be multiplied by quantities which involve the 1D strains. Okay? So in a general sense, in terms of the deformation quantities, it will still be, all terms will be purely quadratic, they will all be square kind of terms, but just that some involve warping linearly and some involve warping quadratically, and that's the reason why this is important. And again, some of these properties, as I said, can be utilized over there, though they look very trivial and quite straightforward. Some of these can become useful properties in order to do a lot of simplifications later. So now we'll apply this VAM example to a very simple problem over here. I will first apply to this problem, and then we can continue with the beam application in the next class, even though we might shoot a little bit over time here. Okay, so first of all, we're looking at the zeroth order approximation. Suppose we have a general quadratic functional I of u comma a, the way we introduced it in the previous slide. Just the only difference is that in this functional we are able to identify its dependence on certain small parameters which you have identified by the yellow colored quantity a over here. So, and again the sign doesn't matter, I've used a minus or plus, it really doesn't matter then. Okay, so in a linear space M is where the u's basically belong to that space M, so that's why the same color code over there. And then the E of u comma v comma a is a positive definite symmetric bilinear functional of u comma v. This is given to you in the problem, let's say. And let's say L is a linear functional of u, as is evident over there. Now we consider certain functions of A, we call them as epsilons, epsilon 4, 3, 2, 1, etc. And each of them is such that the higher number subscript is smaller compared to the lower number subscript. So in other words, basically we can look at refined theories of each of these levels as we go from one to the other, from the right to the left, we go to more and more refined theories. That is the intention. So now we assume that each of these two parts of the functional, one which is purely bilinear and the other which is linear. So basically each of these can be written separately, because remember in the VAM, the general procedure we already saw, what we have to do, we have to expand this out in terms of its leading terms and the next higher order terms, etc. Right? So now it is made out of two parts, so we can break each one of them in general into different orders of magnitude terms. So epsilon is E, for example, can be broken up into E naught, which is the leading terms of E, and then terms which are of the order of epsilon 1 of A, and then etc. Some of these could go to 0, it doesn't matter. So it doesn't need to have in both all the terms. Okay, it could so happen that L1 is 0, but still E1 exists. So it doesn't matter. Okay, so but this is the general way in which you can, let's say, expand out your E and L And then you can see that your leading terms should be of the order of this. So basically your new functional that you're going to set up, which is I naught, will consist of these two terms. So your E naught of u comma u is a positive definite functional, E naught of u comma u, and this is greater than 0 if u is not equal to 0. That is obvious from the fact that E is defined in this way. So its leading terms have to have that property. If the leading terms themselves don't have that property, in the general case it is possible to always find exceptions to this particular situation. So therefore the leading terms would also have this particular property that they are positive definite functional. Next, the first approximation u naught to the minimum point of the original functional will be the minimum point of the approximate functional, the first approximation that you have, which is I naught is equal to E naught minus L naught. So we have to determine the stationary points of that. To determine the stationary points, we have to take the variation of that to first variation of that and set it to 0. So delta I naught is equal to 0, which translates to taking the derivatives of I naught with respect to the u's and then multiplying the variation of u and setting it equal to 0. So now we can substitute for I naught in terms of E naught and L naught, which is basically over here, E naught minus L naught. So once we do that, you basically get this expression. So this becomes the Euler-Lagrange equation for u naught, which can be further simplified into this particular thing, because remember that E naught is a bilinear functional. So when you take the derivative with respect to u, you're basically going to get a factor of 2. And if you rope in this delta u and call it as, let's say, some u bar, you can go back and write that derivative once again in terms of the functionals that we already have, in terms of which we defined E, and therefore you can see that it's quite clear that 2 E naught u naught of u naught comma u bar minus L naught of u bar. So this will just become the delta u quantity. So you have certain linear terms over here. When you take the derivative of that with respect to u and multiply by delta u, you have just constant multiplying delta u, and that delta u is what we are now calling as u bar. And so it's quite clear that that can be written symbolically as just L naught of u bar. So this is the Euler-Lagrange equation that you end up with for the approximate functional that you have created with the leading order terms. And yeah, so this could be any arbitrary element of some set M that we are talking about already in the original, defined for the original functional. Now in the previous slide we had this Euler-Lagrange equation. So let's see what we can do further with it to refine the theory. So we will perturb that solution of u naught, which we get by solving this equation, let's say, as u naught plus terms which are of next higher order of magnitude, which in terms of those gradations that we had happens to be the epsilon 1 terms. So we'll explicitly pull that out so that we have some kind of a bookkeeping parameters. It becomes easy for us to sort out the terms. So we put that epsilon 1 separately. So this is basically together what we call as u1. So that u1 we are taking out epsilon 1 of a explicitly and putting it as u star, where u star is defined as u1 divided by epsilon 1 of a. So now we keep in that original functional the leading order terms in terms of the new quantity which is yet undetermined. So this is already determined. We can solve this equation, we can get u naught. The only unknown now which remains is u star. So to determine u star in terms of u naught, we go back to the original functional, not the approximate functional but the original functional. We substitute there u as this particular quantity, and then we once again take the leading order terms over there. So containing u star, including interaction of u star and u naught. So then basically in the above Euler-Lagrange equation that you have over here, we can choose u bar, because u bar is any arbitrary element of M, we can choose it to be that u star itself, which is the perturbation that basically we are interested in, except for the fact that we have extracted that out. So basically you can set u bar to be u star, and then you can basically see that that equation then boils down to this. All that we have done is replace u bar in both these terms by u star. So this equation is used later on, as we will see in this slide itself, for simplifying, because there will be a large expression that we have when we are trying to determine u star. So we can take advantage of Euler-Lagrange equations that could have occurred in the previous step, that is in the original solution or the leading order solution. So this we will keep aside for now, and then go ahead and do what the variation asymptotic method general procedure lets us to do according to the what we had a description earlier on. So now this is your original functional. So in that original functional, you basically have now the leading order terms for which you have already taken care of. Then we go into the next higher order terms, which involve the E1 and the L1, and which are of order of magnitude epsilon 1 of A. And then there will be other terms which are higher orders of magnitude. So then we substitute for u as u naught plus epsilon 1 u star over here, both on the left hand side and on the right hand side, and basically this is what we get. Now we take advantage of the fact that this is a quadratic functional which consists of a bilinear functional and a linear functional. It has certain properties, remember. So in terms of some constant multiplying function, then that can be taken out, or the functional of a sum basically is the sum of the functionals, etc. But here we are having in two places, so it has to be done in steps. So you can verify that, you can go through those steps, and eventually you will see that it boils down to a large number of terms, and in those terms you will also see that these two terms exist. So we will take advantage of that, and those two terms we can take together to be equal to 0. Further simplification will occur. So we use those properties that we already introduced in the previous slide about linear and bilinear functionals, and to solve for the minimum point u star by setting the variation of the leading terms of this, we are interested only in the leading terms of this, by setting that to equal to 0, we will be able to solve for u star, and we minimize the following. In order to do that, we minimize this functional I star, which basically now involves epsilon 1 squared, because you see that epsilon 1 is going to come out of this. The leading term, of course, will involve an E1 of u naught comma u naught, that does not have any u star. So therefore, those terms, even when we take the variation, it's going to go to 0, so we drop that. We are only interested in terms which have u star, and those will involve quadratic in u star, and also they will involve linear in u star, because this will interact with this, and also of course you will have contributions from this which are directly linear in u star. So again, these terms are of no interest to us, L naught of u naught and L1 of u naught, etc. So all those drop out. So only terms of interest which constitute the new functional for us, I star, are basically those which involve u star and which are all of the order of magnitude epsilon 1 squared. Okay. So remember that the u, the perturbation was epsilon 1, but the I star, the terms which are going to be of next importance are not epsilon 1 but epsilon 1 squared. That is because we are dealing with a quadratic functional, and we have a similar situation when we go to the strain energy, because it's quadratic in the strains and therefore the warpings, and therefore you would see that whatever order of magnitude perturbation you take in the unknown variables, you would have the square of that in terms of the leading order terms that you have to take for the next order of approximation. So this has to be minimized, which means that the first variation of delta I star has to be set equal to 0, and then the Euler-Lagrange equation for u star will arise out of that, and we determine the u star from the Euler-Lagrange equation so obtained.
So in that case, I guess since we have this definition of magnitude and all, so we should call that linear non-linear space instead of linear space, I guess, because we have this concept of magnitude of functions and all.
Yeah, but anyway, we are dealing with positive definite functionals, so probably it is not essential, right?
Not sure.
we can discuss that later. Okay, so now let's conclude this simple example. It's not a structures example, but a general quadratic function example, but directly applicable to our problem because the strain energy function is also a quadratic function. Okay, so let's conclude this particular example. In an asymptotic sense, the correction that we have, epsilon 1 times u star, is less than the first approximation that we had. In many situations, this will be called instead of first approximation as the 0th order approximation, okay, because of the fact that it involves epsilon naught of A, or in other words, it doesn't depend on A at all. So in that sense, this is the leading term. So in many situations, it's called the 0th order approximation. But in a literary sense, this is the first approximation that we got. So that's basically what this means. So and the next approximation that we get is smaller compared to that. But note the order of terms in the functional of the previous slide. So this I already discussed you is of the power 2 rather than power 1. So which means that the goal to obtain functional asymptotically correct only up to epsilon 1. So remember that it's not that your original I did not have epsilon 1 power terms. It had the terms which didn't depend on A, it had terms which are epsilon 1, which it had terms which are epsilon 2, epsilon 3, etc. But the terms that were essential in order to determine the u star or the Euler-Lagrange equation governing u star were only the epsilon 1 squared terms. So in other words, even though you might have to, let's say, get the energy up to only order epsilon 1, in such a situation, you don't need to actually get u star because u star only makes contributions which are of the order of epsilon 1 squared. So if your original goal is to determine the energy functional, let us say, accurate only up to the first order in the epsilon, that is epsilon 1 of A, and not up to epsilon 2 of A, then it's not even essential to get u star. So you already got that because all of those are going to depend only on your u naught, and without solving for u star, you can get the solution up to the next higher order approximation in the functional. So to obtain the functional asymptotically correct only up to order epsilon 1 of A, it's unnecessary to solve for u star as the leading terms associated with u star are of the order of epsilon 1 of A squared as is seen in this equation. The fields to which one can apply VAM are growing continuously, and but of course, as far as elasticity problems, especially applied to dimensionally reducible structures like beams and shells, it's very well established, and a lot of validation studies have been done with three-dimensional finite element analysis as well as other kinds of theories which exist, as well as a few experimental studies done by other researchers. So it's a fairly established procedure. And in the next class, we will take up an example where we directly apply this VAM to the beam problem and see how this overall procedure works in that particular case. Thank you.